In the early 2010s, the software industry embraced a new mantra, polyglot persistence. The idea was simple and seductive. Use the best tool for the job. If you have relational data, use Postgres. If you have unstructured documents, use MongoDB. Need a fast cache? Add Redis. Full-text search? Spin up Elasticsearch. Graph relationships? Neo4j. On paper, this architecture looks like a masterpiece of optimization. You are matching the specific data structure to the engine optimized for it. But as systems aged, a harsh reality emerged. This architectural elegance came with a massive hidden tax. We weren't just building a feature, we were building a distributed system coordination problem that most teams weren't prepared to handle. Today, we're seeing a massive shift back toward the one database philosophy. Every new database engine you add to your stack isn't just a container, it's a lifelong commitment. You now need to manage 4 different backup strategies. You need 4 different monitoring setups with unique metrics and alert thresholds. Security patches must be tracked for 4 different ecosystems. But the most painful part is the mental model. Your developers now have to master 4 different query languages, 4 different driver behaviors, and 4 different ways that connections can fail. This cognitive load slows down every feature release. When you choose polyglot persistence, you aren't just choosing a database. You are choosing to hire more DevOps engineers and spend more time on maintenance than on building your product.
The most dangerous trap of polyglot persistence is data consistency. In a single database, you have ACID transactions. You either save everything or nothing. But when you split data across a relational DB and a search engine, you lose that safety. Imagine a user updates their profile. You write to Postgres, but the network blips before you can update Elasticsearch. Now your database says one thing, but your search results say another. To fix this, you have to implement complex patterns like the outbox pattern or 2-phase commits. You've essentially moved the complexity of a database engine into your application code. You are now responsible for manual data reconciliation, a task that is notoriously difficult to get right.
The reason we can return to a single database is that modern engines have evolved. Postgres is no longer just relational. With JSONB, it handles document data as well as MongoDB. With pgvector, it handles AI embeddings. It has built-in full-text search that rivals specialized engines for most use cases. By using one powerful engine, you get cross-model consistency for free. You can join a JSON document to a relational table in a single ACID transaction. You eliminate network hops between different services, which often results in better performance than a best-of-breed stack that's crippled by network latency. Simplicity isn't just easier. In many cases, it's actually faster.
Engineers often worry that a single database won't scale, but they forget the network tax. Every time your app has to talk to a different database to fulfill a single request, you add 10 to 50 milliseconds of round-trip latency. In a consolidated database, that same operation is a local join or a subquery that takes less than a millisecond. For 99% of applications, the bottleneck isn't the database engine's speed, it's the speed of light between your microservices. Start with 1. Scale when you actually feel the pain, not when you anticipate it.
The goal of architecture isn't to use the coolest tech, it's to deliver value with the least amount of friction. Choosing one database allows you to focus your limited innovation tokens on your product's unique problems, rather than on reinventing data synchronization. Master one tool. Understand its indexing, its locking, and its query planner deeply. Only when you hit a hard physical limit of that engine should you consider the complexity of a second one. Most of the time, one database is all you need.